In this lecture, we'll talk about how to analyze an algorithm. This is relevant. You might not know what the algorithm is doing. This happens in machine learning. You've built an algorithm, but you don't know how long it'll take. That's what analysis of algorithms is, to understand that. So the first thing you have to ask yourself is, what is a good algorithm? Now, this can have two different things. How long would the program take? Why does the program run out of memory? And maybe also, is it readable? That's less important, but it's important for what you do. So to analyze an algorithm, we think of it like, what happens if you know nothing to the algorithm? You're just given something. You do the scientific method to observe it. You observe, then you make a hypothesis, then you make a prediction, then you verify if your prediction works, and then that validates the hypothesis or disagrees. This seems odd. How can you have an algorithm you don't know? Well, a lot of companies will not give you their algorithm. They'll give you the end product, but they won't give you the actual algorithm. So you just have to test it by speed. So that's why the first thing you ask is, how long does it take? Now, not how long does it take for one example. You have to do many examples. How long will the code take for the different numbers, so for different examples? And how many operations did it perform? This is deeper, and you can make a prediction about that. And there are 3 steps in the analysis of the algorithm. So let's think of our for loop. We know everything to do with it, so it's a good place to start. We have our pseudocode, sum is equal to 0 for i is range 0 to 5, sum is equal to sum plus 1. Yeah. Now, here's our flow chart as before. How long does this take? One operation to the sum is equal to 0, and it's 5 operations for the for loop. Okay, so that means 6 operations in total. So time taken, if you put n is equal to 5, is equal to 6. Yeah. Now, how many times for 10 operations? 10 loops. So sum is equal to 0 is 1 operation as before, and then this loops 10 times, so 10 operations, so 11. And so this generalizes to Tn. So if you change that to be n, it's n plus 1. Yeah. And that's where we get this graph here. If you put n is equal to 0, it'll take 1 operation. N is equal to 1, 2, and so forth. This is called linear because it's just a line. Yeah, a line of slope 1. Here is our generalization. You change this such as 1, n plus 1. Very straightforward, very reasonable. Now, what about, how do you generalize this? Like, what about different computers? Well, we don't really care about this. You can say, oh, the first block would take t1 seconds, next block would take times t2. This is how you generalize it, and you find out for each computer how long each of these would take. But actually, in algorithmic world, all you care about is n plus 1. You don't care if that's a nanosecond, 1/10 of a nanosecond, a minute. You know that there's a relationship. Yeah. So for linear operations, it does not matter what this plus 10 is or plus 1. If n gets large enough, none of that matters. So if you have to do 5 operations, so let's say n is equal to 5, then that algorithm takes 6 operations. This would take 106, and this would place 5 plus c. But when we have 10 to the 9 operations, yeah, does it matter what size the 1, 100, or c are? No. Yeah. So total time for one of these is called approximately n. It just, for every single time you add something, it just adds 1 extra go of it. Here we are. We have a linear operation between 0 and 100. And you see they're separated by 1. That's kind of, you can see there's 2 lines there. But when we go out from 0 to 1,000 here, There's no difference between those lines, and there shouldn't be any difference between those lines, because if you're doing something 1,000 times and you have to do 1 at the very beginning, does that 1 count? No, it doesn't matter. So now we come back to the more complicated double loop. So with the double loop, so here's our example. A double loop is a loop in a loop. So we have a first loop is a length 3, and in that we have a loop as well. We've gone through examples of this in class. So what you have here is you have to do the inner loop 1, 2, 3 times, and then you do it again 1, 2, 3, because the outer loop tells you to do it again, and then you do it 1, 2, 3. So what we have here is this one's going 3 times, but it's telling the next one inside goes 3 times. So what we have is 3, yeah? 3 by 3. What's happening here is that 3 and that 3 multiply by each other. So in theory, you could write the order of this is 1 plus 9 plus 3. Actually, 1 plus 9 would be reasonable. So what happens when we go a step further and say for 5? Or that should be the 5. What we have is 1 plus 5 plus 25. So that means with a double loop, whatever that number is, it's squared. So that gets very, very, very slow very quickly. So if you have to do 1,000 operations, 1,000 n, the algorithm would take 1,000,000, 1,000 squared. And so here we see a very simple example of 10. It's not so bad. Okay. N is 1 is 1, n is 2 is 4, n is 4 is 16. And then we go out to here and we're talking about 100 for it to do something, to tell it to do an operation of 10. So in my example here, the generalized form is n squared plus n plus 1. It's quadratic. And this n squared term, which is our double loop, dominates. It is the biggest one. It's the one that takes up all the information. It's the one that takes all the time to do. So once again, it's not so important, but if you have different time periods for each of these operations, use multiply by. But really, all the work is the inner loop. Yeah, you have to do that again and again and again and again. So this means that, let's take, for example, Facebook. If it's searching for something, it wants that search algorithm to be of order n because that's fast. But if it has to go through everything twice or n times, and you have 1 billion users, that's 1 billion squared. And that becomes computationally almost impossible. Well, slow anyway. So now we have the general order of growth. The fastest algorithm you can have is called a constant of order 1. That just means you'll always do the same amount every time it does it. Doesn't matter how many operations, how big n is, it'll always do the same number of operations. Log n, we'll see in a second, but that's quite fast. So it's log base 2 n. Linear is the one we've just spent a bit of time with. That's exactly what it is. It's like a line. N log n is a bit slower. N squared, as we just said, that gets very expensive. And then n cubed is too expensive to even bother with. And exponential is, well, insanely expensive. So here's just a couple of plots of the comparison. On the left, n is between 0 and 10. On the right, n is between 0 and 100. And what we see with a constant, maybe it costs a bit more early on for a low number of trials. But as we push out further and further, as n gets larger and larger, a constant is a much better thing because it's just always going to be the same amount of effort. Now, the comparison between linear and log linear. Log, the blue, is faster. So it takes less operations. And as it keeps going out, it becomes more apparent that it's much quicker than linear. Now, we have linear and linear arithmetic, which is log linear. So we see the red is linear, and then we see the log linear looks less, but as we push out to higher n, Log linear gets higher and higher and higher. So linear is better. Now, between quadratic and cubic, this illustrates when you have quadratic, within 10, you have 100. Yeah. But with cubic, you have 1000. It's hugely different. When you even go out to 100, you can't see the quadratic anymore. It's so small in comparison to cubic. Yeah. So a cubic algorithm is something you don't want. And then as we go out further to exponential and things, it gets harder and harder. So as I say, this is the order of growth from fastest to slowest. If your algorithm is exponential, it's unbelievably slow. So you can only do small operations. Yeah. Now, you don't want the exact, you just want an approximate. You don't want the exact numbers, you just want to approximate the numbers. So that's why if something's quadratic and linear, so here, once again, between 0 and 10 on the left, between 0 and 1000. So between 0 and 10, there is a difference in quadratic linear, quadratic plus linear, and quadratic. That's one graph is n squared plus n plus 1, and the other graph is just n squared. Yeah, that's different to two graphs. But what we see here is they look a bit different here, but when we zoom out far enough, you can't tell the difference between the two graphs. They look identical. So does it matter if it's n squared plus n plus 1 when n gets large enough? No. These would both be of order n squared, or just n squared. And that's where the tilde term comes in. Approximately, order of an algorithm. So if you have a quadratic algorithm that's n squared plus 1 or n squared plus log n plus the thing, you just say n squared. What's the biggest term here? What's the biggest term? N squared. And even if it's multiplied by a constant, you don't care about that. It's the n squared that gives it the cost. Same with cubic. What's the biggest term? The cubic term, the cubic term, the cubic term. Everything else is less than that. So the algorithm is of cubic length. That's how you analyze an algorithm. You find out which costs the most to do, and that's the cost of the algorithm. That's the general tilde, which is approximately the cost of the algorithm. So in the next lecture, we're going to actually see if we can get what those numbers are, figure out is it quadratic, is it cubic, by doing log transforms.